In the last two lectures, we took a scientific question and we refined it into a research question that we can answer by collecting and analyzing some data. And we made some decisions about the design of the data collection. So now let's pretend that a year has passed and we've got our data. Let's take a look at it. Let's start with a quick reminder of where we are. We're looking at the Canadian Trial of Dietary Carbohydrates and Diabetes. We're looking at people with type 2 diabetes, and we're giving them a high carbohydrate diet. Some of them have been assigned to follow a diet with high glycemic index foods, and the rest will be taking a diet with low glycemic index foods. Our primary objective is to see the effects of these diets on blood HbA1c concentrations, which again is a measure of diabetic control. As a secondary objective, we're interested in the risk of heart disease, so we'll look at the level of C-reactive protein in the blood. In addition to diet as an explanatory variable, we'll also take a look at sex, age, and BMI of the subjects. And we're working through these steps, the process of statistical inquiry. In this video, we're going to take our first look at the data. We'll be covering both Step 3, where we'll use this first look to see if there are any problems in the data, and part of Step 4, some of the preliminary analyses. Here are the first few lines of our data. Although you can't see them all on this screen, there are data values here for 103 subjects, so there are 103 lines of data in our data file. You may recall from the last lecture that we said we needed to recruit 106 subjects. But we expected a number of them, about 20%, to drop out, which would leave us with only about 88 subjects. But we have 103. The actual study is a little more complicated than what we're presenting here. And it needed to recruit a few more subjects than we calculated in the last lecture. Now we're working with the actual data and the actual number of subjects for whom data were collected. So now let's take a look at the data. Note that sex is coded F for females and M for males. Then we have the subjects' ages and BMIs. These were measured at the beginning of the study. Diet is coded L for the low glycemic index diet and H for the high glycemic index diet. The columns HbA1c and CRP are the values at the end of the study. So these are the values after 1 year on the treatment diet. Some of these other variables you might not have been expecting to see. The variable fail is Y or N for yes or no, and it's an indicator of treatment failure. The yeses are subjects who met the inclusion criteria for the study, but then they needed to drop out because their medical advice changed and they were put on medication to control their diabetes. And you might recall that one of our inclusion criteria was to only study diabetics who were being treated by diet alone. These subjects who are considered failures all have relatively large values of HbA1c, but the decision to drop them out was based on more than just that, so they're not just the highest values that we see in our data. An interesting question is whether or not the number of subjects who were treatment failures existed equally between the two dietary treatments. And we'll come back to that later. Something else to note is that for our outcome variables, HbA1c and CRP, we also have baseline values. That is, these are measurements taken at the start of the study, just before the subjects started on their dietary treatments. And we'll talk later about dealing with these. We'll start by looking at our variables one at a time. The purpose of this is to identify any obvious errors in the data and identify features such as possibly outliers or skewness that may affect the choice of the analyses that we carry out. Let's start with our categorical variables: diet, treatment failure, and sex. We'll just look at tables of frequency and relative frequency for these variables, since each of them has just two categories. For diet, we can see that our randomization process resulted in slightly more subjects, 53%, receiving the low GI diet. Only 5 of our 103 subjects were considered to be treatment failures, that is, they needed to withdraw because they went on medication. And for sex, we see our first potential problem. Some of the males were inadvertently coded with a lowercase m. But we can fix that, and then we can see that the recruitment resulted in 58% males and 42% females. Now we can take a look at our quantitative variables. They are age, BMI, HbA1c, measured at the end and at baseline, and CRP, also measured at the end and at baseline. Starting with age, we can see that there's something funny going on here. There's a huge outlier, which is an age close to 1,000, and clearly a mistake. Flipping through all our quantitative variables, we see the same phenomenon for BMI and HbA1c at the end of the study, although not for HbA1c at baseline. And here it is for CRP, both at the end of the study and at baseline. A closer look at the data shows that there are several values entered as 999. These are actually missing observations. For some reason, the measurements for these quantities on these particular subjects were either lost or unable to be measured. The indicators for missing values are different for different statistical software packages. So sometimes people code them with impossible values and leave it to the analyst to adjust them to what they should be for the software that they're using. And we'll need to do that before we can continue. Here are the counts of the number of missing values for each of our variables. If the missingness happens completely at random, then, although it limits our ability to use the observations in our analyses, we don't have to worry about them biasing our results. But if the fact that they're missing tells us something about what the values would have been had they been observed, perhaps say HbA1c is missing because it is large, then we call those missing values informative, and having them in our data would bias our results. For example, our estimate of the mean of HbA1c would be smaller than it should be, because we're missing those large values. There are advanced methods to deal with missing values that are informative, and there are also methods for imputing estimates of missing values. For the actual CCD study analysis, some of these advanced methods were used. But for us, a quick count of the missing values in our outcome variables at the end of the study shows that the missing values occur in about equal numbers in the two diet groups. And we'll assume that they aren't informative, and we'll just carry out our analyses using the observations that we have. So now we've cleaned our data by fixing some problems with the coding of sex and by replacing the 999s with the appropriate missing value indicator. Now that we've got rid of those 999s, let's go back and take another look at the quantitative variables. Looking first of all at age, our subjects ranged from 40 years old to 74. Our inclusion criterion for age was 35 to 75 years. So we didn't recruit any subjects quite as young as our lower limit. The distribution of BMI is a little bit right skewed. Our inclusion-exclusion criterion for BMI was 25 to 40 kilograms per meter cubed. And we have subjects just outside that range, probably because their BMI changed after they were initially screened for this study. Moving on to our primary outcome variable, HbA1c, we can see that it has a fairly symmetric distribution, and you should be able to see that symmetry in the 5-number summary as well as the histogram and box plot. In this course, we've learned inferential procedures based on the normal distribution, and that seems like a reasonable model for HbA1c. And now we can take a look at the distribution of HbA1c at baseline, which is also fairly symmetric. Of course, we're not really interested in HbA1c at baseline, but what we're interested in is how the subjects changed during the year on their study diets. Here are the box plots of HbA1c at baseline and at the end of the study, side by side. On average, HbA1c may be slightly higher at the end of the study, which is not what we wanted. But there's lots of overlap in the boxes, so we don't expect this to be statistically significant. That said, there's a fundamental problem with this plot. The same subjects have an observation at both baseline and the end of the study, but the plot doesn't match them. For matched data like these, you may recall that we can look at the difference, in this case the change from baseline. Here are the differences in HbA1c, calculated as the value at the end of the study minus the baseline value. The lowest values are negative, but since the first quartile is positive, we know that more than 3/4 of the subjects had higher HbA1c at the end than at the beginning of the study, with a few very large positive changes. An even more useful representation is to look at these changes in HbA1c by diet. It seems that the highest values are for the low GI diet, and the median and the mean are also slightly higher for the low GI diet. But again, there's lots of overlap in the box plots, so these differences may not be statistically significant. Looking now at our outcome of secondary interest, CRP, we can see that it's very right-skewed. In the box plot, the long right tail in this distribution shows up as a trail of observations beyond the upper fence. Right-skewed distributions often happen in cases like this for variables such as CRP, which are bounded below by 0, but have the potential to be very high. At baseline, CRP has a similar right-skewed distribution, clear in the histogram and the box plot and the 5-number summary. There is one observation that is quite far out in the tail. But this can happen with right-skewed distributions, so rather than calling this an outlier, it's more likely that it's a consequence of the shape of the distribution. In the regression lectures, we saw how a logarithm transformation can be useful in creating a linear relationship. Because of the shape of the logarithm function, logarithmic transformations bring in long right tails. So they're also useful in situations such as this one. Again, we'll use the base 10 logarithm. And here are the plots and summary statistics of CRP at the end of the study once the base 10 logarithm has been taken. You'll note that it's much more symmetric, and as a result, we should be much more confident using inferential procedures based on the normal distribution. This is also the case for CRP at baseline. The logarithmic transformation changes what was a very right-skewed distribution to one that is symmetric and bell-shaped. Working some more with the logarithm of CRP, and as we did for HbA1c, our other outcome variable, we can combine the baseline and end-of-study measurements of CRP by taking the differences. So we'll take a look at the difference or change from baseline in the log of CRP. Taking you back to some basic facts about logarithms, the difference of two logarithms is the log of the ratio. So the difference between the log of CRP at the end of the study and the log of CRP at baseline is the log of CRP at the end divided by CRP at baseline. So this difference in the log measures the log of the ratio. If CRP at the end of the study is equal to CRP at baseline, so then there's no change in CRP from baseline over the course of the study, then the ratio is 1. And you may recall that the log of 1 is 0, which of course makes sense. The difference should be 0 if there's no change. Our box plots here are showing the differences of the log of CRP by diet. And for this variable, there does seem to be a difference between the two diets. Note that the median and the mean are negative for the low GI diet and positive for the high GI diet, although quite small. This indicates that, On average, CRP seemed to drop for subjects on the low GI diet, but not for the high GI diet. Lower CRP is good. It means less inflammation. So here we seem to have an indication that the low glycemic index diet is having a beneficial effect that we don't see in the high glycemic index diet. And we'll want to see if that is statistically significant. One more thing to note before we leave these plots. There is both a large and a small outlier for the change in the log of CRP for the low GI diet. Later on, we'll investigate the effects of these two observations. And as the final step in our initial look at the data, let's see how the other subject characteristics that we've measured, that is sex, age, and BMI, are related to our outcome variables. Looking first at HbA1c, and we'll keep looking at how it changed from baseline. The values for males seem slightly higher than the values for females, but this doesn't look to be significant because the box plots overlap so much. For age, since it's quantitative, we'll look at a scatter plot, and there doesn't seem to be any indication of a relationship. For BMI, it appears that it may be the case that subjects with higher BMIs have larger changes in HbA1c, and we'll need to come back to that. And for our other outcome variable, the change in the log of CRP, other than the outliers, the values are very similar for females and males, and there doesn't appear to be a relationship with age, nor with BMI. So now we've made a lot of progress. We have clean data, we've made a decision to work with the log-transformed CRP, and we know a few things to watch for, in particular a couple of outliers, and the possible relationship between HbA1c and BMI. In the next video, we'll focus on our primary and secondary objectives, and we'll carry out formal inferential procedures to see if any of the differences that we've observed here in our preliminary analyses are statistically significant.